And the Maltese language has quite a lot of Arabic. You just pronounce it funny, but it is actually North African, but written in Latin words. So it was very funny for me when I was here in 2017, because I pretty much could understand most of what people are talking about. I could read signs, and I was like, am I in Europe? And now, like right now, you all confirmed how close Malta and Morocco are together, because you all showed up a couple of minutes late. So I feel home. Right. Well, hi everyone. My name is Abdel, or Abdel Fattah is my name in Arabic, but I've been living in Europe for 11 years, and no one can ever pronounce my name ever, so I decided to just go by Abdel as a nickname to make everybody's life easier. I work for Google. I'm a developer advocate, so my job is really to go to conferences and talk about stuff. Most of my thing I do is Kubernetes related, hence the t-shirt, and I also co-host a podcast called the Kubernetes Podcast by Google. And today we're going to talk about Ray on Kubernetes. I'm going to explain what Ray is, and then explain why Ray works on Kubernetes very well. But before I get going, how many people here know Ray, have heard of Ray before? Zero, good. How many people know Kubernetes? Okay, few people. Good. Great, awesome. So we'll focus a little bit on Ray. So, you know, AI is all around us. Everybody's doing AI these days. We actually just published a podcast episode recently, I just think yesterday or the day before, about Spotify and how they built their own ML platform, which uses Ray as one of the components. And because it's Spotify, everything at Spotify has to be music related. So the ML platform is called Hendrix. Jimi Hendrix, the singer. But like all these companies that you see here actually use Ray. They use it to some extent. And that's because, you know, since last year, ChatGPT have taken the tech industry by storm, and everybody now wants to do LLMs. And pretty much all conferences, I've done about 50 conferences so far this year, up to now, and pretty much all of them are some form of AI oriented. Everybody wants to do AI, everybody's crazy about AI. This talk is not really about AI itself, it's about Ray. So it's about the practical side of AI, or how to do MLOps with Ray, right? And so what are we trying to solve with Ray? So Ray is trying to solve a very basic problem that most people that are doing machine learning or data science have. Is the fact that the ecosystem, the open source ecosystem of machine learning is extremely fragmented. So in order to do anything related to data and ML, data scientists and machine learning engineers have to learn multiple tools. There is one tool to do data preparation, there is one tool to write your pipelines, there is one tool to do training, one tool to do fine-tuning, and these are all different open source projects, different tools, they function differently, and they might also have their own programming languages. Most of what people do in data science is Python, but there are some stuff that people can do in Java. And so solving the problem of tooling, or giving people a single tool so they can do a lot of the stuff they need to do using a single platform, solves the problem of cost, because then you don't have to relearn things, right? If you have a company and you're a very small structure and you lose somebody, then it's easy for people to grab whoever else code and just work on it instead of just having to learn a new thing. Solving the problem of scale, which we're going to talk about quite a lot today, and also making things kind of future-proof in the sense that if you write today an ML pipeline, that ML pipeline should work in the future with no changes. So Ray is a framework written in Python that tries to solve this fragmented problem by giving you a single tool with multiple libraries that can be used across the entire life cycle of machine learning. So inside the pipeline itself, you have 5 group of libraries. There is Ray Data, which is a libraries for doing data preparation. There is Ray Train, which are libraries for training. There is Ray Tune, which are libraries for tuning or fine-tuning. There is RLLlib, which is reinforced learning libraries. And then there is Ray Serve, which is the last component you would need, because basically that's what you need to actually run a model, right? Once you have trained the model and fine-tuned it, you want to run it, you can run Ray Serve. So all of these are part of the Ray framework itself. It's all Python, all open source. Then there are some core libraries, they call them Ray AI libraries. Those are like the core libraries shared across all these different components. You can actually install all of them, or you can install only one. If you are a Python developer, you're familiar with pip install, whatever. So you can do pip install Ray, which will install all of Ray, or you can do pip install Ray between brackets Ray Tune, which will install only the fine-tuning libraries, for example. Then once you have written your code using Ray, you need to run that code, right? And so that's where Kubernetes comes into the picture. Ray itself, or the people who built Ray, by the way, Ray came from Stanford. It was a research project inside the Stanford University. They were trying to build a framework to do HPC, high performance computing, and eventually they made Ray open source. And the people who actually built Ray left Stanford and created a company called Uniscale. And today Uniscale is one of the biggest contributors to Ray, but they have contributors from other companies. As far as the community itself is concerned, they don't really care where you run your code. They make Ray very agnostic, and you can later run it on top of virtual machines, you can run it on top of Kubernetes, or you can do whatever you want with it. I'm going to talk about that in details. So you can think about it as like 3 layers. You have the libraries on the top, which can be used to do all the machine learning related tasks that you need. One of the downsides of Ray is the fact that there is no straightforward way to migrate from whatever you are using to Ray. If you are writing Python code, you will be able to reuse your code to a large extent. But if you want to use Ray, you will have to rewrite your code to use the Ray libraries. Like there is no straightforward way to migrate from, let's say JAX, for example, to Ray. Then you have the Ray core, which is the core components, and then under that you have the cloud layer, and the cloud layer is essentially where you run your code. So the community that builds Ray, they don't really write anything related to cloud. They focus on building the core Ray framework. Then it's up to each cloud provider to actually build their own integrations, as we call them. So there is actually an integration to be able to run Ray on top of AWS. There is an integration to run it on Azure. There is an integration to run it on Google Cloud. And there is an integration to run it on Kubernetes, right? And all these integrations are maintained by the cloud providers, not by the Ray community. So in other terms, what you could do is you could write Ray code, and in order to run it, you can, for example, pick the libraries that are integrating with AWS, and then you would implement them, and that will spin up AWS resources, so EC2 instances, and then push your code there and run it for you. So yeah, single framework to be able to ingest data, do batch workloads, so training and fine-tuning, do distributed training, and do the serving part. And it does integrate with a lot of other components. It integrates with Hugging Face, so you can actually use Ray to pull a model from Hugging Face if you want to run it. It integrates with PyTorch, it integrates with a lot of other tools that people are already familiar with. So let's start getting a little bit into the details. If you are familiar with Python, this might sound like just 2 functions, one function called read array and one function called add. The read array takes as an input a file and returns a value, and the other one takes 2 inputs as integers and calls a function. If you want to run them on Ray, you will have to annotate them or decorate them. So by adding the @ray.remote, that basically tells Ray that these functions will not be executed locally on my computer, they will be executed on the Ray cluster, right? And by doing this, these become what we call tasks. So functions in Python are called tasks in Ray. And you can have multiple tasks, and you can actually, Ray itself has a way to orchestrate those tasks and know exactly how to run them in the order in which they're supposed to be run. As an example, if I do this, ID1 equal read array remote input, so this will execute the read array function remotely on a cluster. So it will push the function code, push the file that needs to be run, and run the code. If I do something like this, where I just invoke the read array again on a remote cluster, it will just run like regular. But if I do something like that, so this will basically mean that I need to be able to execute the first read array for ID1, execute the second one for ID2, grab the output of ID1 and ID2, and then call ID3 to be able to execute ID3. So this execution graph, this order in which the functions will be executed, Ray resolves that for you, so you don't have to worry too much about it. And just doing this very simple thing, you can actually parallelize these functions. So if I would push a code like this to a Ray cluster, if the cluster has more than one worker node, imagine, for example, these files, these input files are like 1 terabyte of data, and they need to be processed. Each function, each file needs to be processed. Then Ray will be able to run 2 functions in parallel, either on the same worker node or on separate worker nodes, depending on the resource availability. And so if you do something like classes in Python, those become actors in Ray. So an actor is just a class, and inside an actor you can have multiple tasks. Just terminology, nothing too fancy. So you can do something like this, instantiate a class, do all of that stuff. As long as you annotate the class itself with the ray.remote, that basically tells Ray, run this function for me, or run this class for me. And so from here, we can do a lot of interesting things. Like for example, if we need to run a function and we need GPU for it, we can just between parentheses on the Ray remote annotation add number of GPU1. This is a very high level abstraction layer that allows developers to define a function and say this function will run on top of a node that has a GPU attached to it. How is that node going to be provisioned? Where is that GPU coming from? What kind of GPUs? That's all part of the cloud layer. That's none of the developer problem. The developer should focus only on writing code and running code, right? So if you're familiar with Kubernetes, this probably will feel very familiar to you, especially if you see on the slide it says Raylet, which is pretty much kubelet in Kubernetes world. So Ray has a very, very similar architecture to Kubernetes, where you have a master node or control plane, and then you have one or multiple worker nodes. They call the master node the head node. So the head node is the component that runs all the logic itself, and that's where you have the API that you will use to push your code to be able to execute it in Ray. Then the worker nodes are just the components where the tasks get executed, like your code will be run, right? So on each of the worker node, you have Raylet, and the Raylet is a component that talks to the head node. So that's how the head node communicates with the worker node to tell the worker node what to do. So it's pretty much familiar with if you're familiar with Kubernetes architecture, you have the kubelet on the worker node, which talks to the API server, and the kubelet receives order from the API server to be able to execute containers. It's kind of the same architecture here. So these components could be virtual machines, they could be physical servers, or they could be Kubernetes pods, right? As far as Ray itself is concerned, it doesn't really care too much. You can do these things however you want to do them. A few things I have to say about this before I move. It does have a global control storage. It's confusedly named GCS, which is confusing for me because the Google equivalent of S3 is also called GCS, Google Cloud Storage. But the global control storage, or the GCS component, its job is to manage storage. So if, for example, the example I gave earlier, where you have to read array as a function and you give as an input a file, then that file will be managed by the GCS component. It will be pushed into the worker node where the code will be executed, and then whatever results of that execution will be collected by the GCS components and then presented to you. So you have a component to manage all the storage part of the jobs. Because most of the time when you are doing machine learning workloads, you use data. And data comes in the form of files, typically, some CSV files or JSON files or whatever. So you have a component that manages the movement of all these files across. Like you are pushing your code and the data to the head node, but the head node has to eventually push that code and that data to a worker node, so the GCS component takes care of all of that stuff. And then on the head node, one of the interesting things to keep in mind is on the head node you have the various APIs. So there is actually a single API where you could just use the Ray. There is a Ray command line, and you can use Ray to talk to that API. So if you want to send a job, you can just do Ray job submit, and then that command line will just take your code and send it to the API server. There are just two observations I have to say about Ray for you who would be interested in exploring it later. Ray itself doesn't have any concept of authentication or authorization. So the API itself, as long as it's exposed and you send stuff to it, it will run it for you. It doesn't really care too much. It doesn't have authentication built in. It doesn't have authorization built in. Which means you have to be a bit careful. If you're running Ray, do not expose it to the internet. You would ask me why I shouldn't expose it to the internet. Well, basically anybody can use your API to run code. And if you are running Ray on top of Kubernetes, it can scale your Kubernetes cluster very fast, which is both a good thing if you're trying to scale your workloads, but a bad thing if somebody's trying to hurt you, right? So if you just expose your API to the internet, people can just use the API, submit random jobs, cause your cluster to scale up, and then you will be paying the bill for those clusters, right? Just be careful of that. Generally speaking, do not put stuff in the internet. I think that this is a very common rule. So, where does Kubernetes come to the picture? Well, Kubernetes itself is actually very good at doing one thing, which is running scalable workloads. Kubernetes, if you don't know what Kubernetes is, it's an infrastructure automation tool. So if you have a cluster or a group or a fleet of virtual machines, and you need to run stuff on them, if you are like me, slightly older with white hair, you are used to the sysadmin time, when we used to write Python code and bash scripts and maybe Chef or Ansible if you are really fancy, to be able to manage like a fleet of machines, right? With Kubernetes, essentially, you take those fleet of machines, you wire them together into what we call a cluster, and that cluster has an API. And that API is what you talk to to be able to do stuff on the cluster. If you want to run a workload, you tell the API, run this workload for me, right? So Kubernetes has one good thing so Kubernetes itself has a couple of good things. One of them is very agnostic. You can run Kubernetes pretty much anywhere. You can run it on Google Cloud, you can run it on Azure, you can run it on AWS. You can use cloud-managed versions, right? The Kubernetes managed by the cloud provider, or you can just self-deploy your own Kubernetes if you are crazy. You can run it on top of your own virtual machines, you can do it on top of VMware, you can do it on like whatever you want, right? It's very good at handling scalability. So Kubernetes itself has multiple autoscalers, we call them. So autoscalers for workloads, autoscalers for nodes. So if you have a container that is running on a cluster and there are like 5 instances, you can basically define an autoscaling configuration to say, if CPU utilization of my workloads go over 50%, just autoscale my workload, add more components, add more containers, right? And if it goes below 50%, scale down. It also has components to be able to do infrastructure layer scalability. So if you are trying to scale up a workload, but there isn't enough resources available in the cluster, then there is a component that goes, oh, I need more nodes, and it will go provision those nodes, create them, add them to the cluster, so that you can run or scale up your workload, right? And this is actually really good for Ray, because Ray follows the same concept. Ray has the head node and the worker node, so if we take Ray and we put it on top of Kubernetes, then we can leverage the auto-scaling capabilities of Kubernetes itself. The self-healing, Kubernetes is very good at doing self-healing, so if a workload dies, it will just restart it. And then we can leverage that with Ray. And so all of this is done through a component called the Ray operator. For those of you who are not familiar with Kubernetes, operator is just a term in Kubernetes world that essentially means a pod, literally. So an operator is essentially a component that will act on an object. In Kubernetes world, you, as a user, you don't really define what the cluster will do. You define intent. You write a YAML file, and that YAML file is what do you want to happen. You don't tell the cluster what to do, you tell it what do you want it to do. You don't tell it what you want it to do, you tell it what's your intent. I intend to run a container 5 times, right? That's an intent. And then Kubernetes will act on that intent and make those 5 containers come up. The component in Kubernetes that does this job is called an operator. It's just a single workload that basically talks to the API server and tell the API server, if this object is deployed, tell me, and I know what to do, right? So we, as in Google, wrote an operator for Ray called kubeRay operator. And so this operator allows you to basically run a Ray cluster on top of Kubernetes and then also run jobs using Ray. So, talked about this. Yeah, so this is where it gets interesting. So the operator itself introduced 3 new components for running workloads. So these are all CRDs, custom resource definitions, if you're familiar with the word in Kubernetes, but essentially you can think about them as object, like YAML file objects. So there is a component called Ray cluster, so it allows you to define a Ray cluster, so you can write a YAML file, Ray cluster, how many head nodes, how many worker nodes, and all that stuff. And once you deploy it, it will spin up all these components for you. There is a component called Ray job, which allows you to create jobs. So in Ray itself, you could just, if you deploy a Ray cluster using the Ray cluster component on top of Kubernetes, you basically have the head node and you have the API, right, from Ray. So you can just talk to it with the command line and then you can run workloads. But if you want to do another higher level abstraction layer, so you don't want people to deal directly with Ray, but you want them to still deal just with Kubernetes, then you can use what we call a Ray job. And a Ray job does what the name says. It runs a job, right? So you will write your Ray job as a YAML file, but under the hood, the operator will talk to the API of Ray to be able to execute the job for you. And then the last component is something called the Ray service, which allows you to run the serving part. So this is where things start getting a little bit confusing. Because in the machine learning world, there are 2 words that people use interchangeably, and they're very confusing: inference and serving, right? I think you probably have heard the word inference before, but sometimes people say serving. So what does inference or serving actually mean, right? It's like, I have a very stupid way, like explain inference for me like I'm 5 years old kind of thing. You can think about serving in machine learning workloads as what a web server does for pages. If you write a website, and you have HTML, CSS, and JavaScript, right? You need a web server. If you don't have a web server, your website is useless. You cannot run it. So the web server is something like Apache or HA proxy or Nginx or whatever, is a component that is standard, and then you can configure it to say, here are my HTML, CSS, and JavaScript files, just run this website for me, right? In the machine learning world, when you create a machine learning model, your model is just a file. It's literally a glorified zip file. It's just an archive file, right? That contains all the machine learning stuff. But that file is pretty useless. Like, you cannot do much with it. You need something to be able to run it. And that's what we call an inference server or a serving platform. And so serving have existed in machine learning for a very long time, but now with large language model, it's kind of have exploded quite a lot. I think the one that we would probably be familiar with, how many here have used Ollama before? Have you heard the word Ollama? No? One person? So Ollama is a very common tool to be able to run local language models, large language models. So you can download Ollama as a command line, you can run it on your laptop, and you could, basically similar to how you do Docker pull image, Docker run an image, you can do Docker pull Llama 3, for example, from Meta, and it will download the Llama 3 model, and then you can do Docker Ollama run Llama 3, and it will execute the Llama 3 model for you, and give you an API endpoint so you can talk to it, right? So Ray service serves the same problem, the same purpose. It allows you to spin up a server that runs a model inside. It could be your model that you have trained and fine-tuned, or it could be a model coming from Hugging Face, or it could be a model coming from Kaggle, or it could be whatever model you want, right? So similar to how Ray cluster works and how Ray jobs works, a Ray service is just a YAML file that defines a bunch of properties, and with these properties you define, this is the model I want to run, and then it will run it for you. So to resume, in Ray world with Kubernetes, you have three objects. Ray cluster, you need the Ray cluster to start with because that's what spin up the Ray cluster itself. And then if you want to do jobs, you can do Ray jobs. If you want to serve a model, you can use Ray service, right? So this is kind of how it could look like as an example. This is where we wrote a class, an actor, with like a dummy function called doWork. And then we basically take this code, push it to the Ray head or the head node. The head node will create the actor, and then it will delegate the execution of that actor to one of the worker nodes. And that's the part of basically orchestration, where it will use the worker nodes to be able to execute all the actors and all the tasks inside those actors. If you do all of this on top of Kubernetes, well, each of these components is just a pod, right? So the Ray head node is a pod, the Ray cluster, the worker nodes are a pod each. And then you have the controller, which runs on the control plane of Kubernetes that does all that stuff. So when you create a Ray cluster, it will run the Ray cluster for you. When you create a Ray service, it will run the Ray service for you, etc., etc. And because all these components are pods, well, autoscaling becomes simple. Because basically you just use the same logic to autoscale Kubernetes workload to be able to autoscale your Ray cluster, right? So if you want to add more worker nodes because you have more jobs that need to be executed, you just take that deployment called the Ray worker and just add more components to it, and it will spin up more pods, right? And then if the underlying infrastructure of your cluster is running out of nodes, then eventually at some, let's say for example you have a cluster in unscheduled, right? They will be just waiting to have available resources. And if you're using a cloud provider, then typically you would have some sort of autoscaler built in, and the autoscaler will look at those unscheduled pods and go like, oh, we need more resources, and just spin up more nodes to be able to run your workloads, right? So autoscaling in Ray becomes the same typical autoscaling problem that Kubernetes is very good at solving. Yeah, so fine-tuning scaling, we talked about that. It's also very good at doing something called bean packing. So bean packing is the concept of being able to fit all these workloads into a single node so you don't have waste, right? And so Ray, or the Ray controller, is actually very, very optimized to be able to bean pack your workloads properly. If you are not familiar with, there are actually multiple other optimizations in Kubernetes that can be leveraged by Ray itself. So bean packing is a very simple concept. You have like a node, it runs like a bunch of pods. The Kubernetes will try as much as it can to fit all your workloads into that node so you don't waste the resources on the node, right? That's a very simple problem to solve. But there is also a lot of other things. For example, in like a very simple example I can give is very recently in Kubernetes 1.27, so a few versions ago, they actually added a feature to be able to live resize pods. So before, when you run a pod on Kubernetes, for those of you who doesn't know what pods is, it's just a container, right? Just don't get confused, it's just a container. So before you execute a pod in Kubernetes, you have a section in the YAML file called resources, right? And in that resources section, you can define CPU and memory. You can say, I want 1 CPU, I want 2 gigabytes of memory, run this for me, right? Before 1.27, in order to change those values, in order to update, add more CPU or add more memory, you had to kill the pod and create it again. So you had to update the configuration file, push it again, and Kubernetes will just terminate that pod and create a new one. In 1.27, they added a feature to be able to live resize pods. So you can actually take a container and just throw more memory and more CPU at it. So that's vertical auto-scaling. So you can just like make a bigger pod, essentially, right? This particular feature can be actually leveraged by Ray. In Ray, you can do vertical auto-scaling for the worker node. So if the worker node is running out of resources, you can just say, give it more memory, give it more CPU, and it will just scale up the pod. Now, you have to be a little bit careful with how you use this feature in Kubernetes and Ray, because as we all know, you can scale down CPU, but you cannot scale down memory, right? Memory is not a compressible resource. So if you have a pod and you auto-scale that pod up, so you add more CPU and memory to it without restarting it, it will work. If you try to remove memory from it, it might die. Because different parts of the memory pages are used in very funny ways, and different programming languages handle memory differently. So it's very possible that you update a pod and you say go from 3 gigabytes of memory to 2 gigabytes of memory, and then your thing will just crash and die. That's because memory cannot be scaled down. So I do not recommend actually scaling down using the feature to do scale down. Just use it for scale ups. Yeah, so we talked about this. You have the serving part. I'm not going to talk about too much into details. Yeah, you can also add GPUs. So with Ray, you could run some Ray worker nodes, so the pods themselves, and then just define an annotation. You just literally add a single a string on the YAML file to say add GPUs, and that will attach GPUs on the node directly into the pod. So if your workload needs GPUs, it can be scheduled on a worker node that has GPUs attached. Make sense? And then yeah, so it integrates quite a lot with a lot of other existing frameworks. So Hugging Face is one of them I talked about. LangChain is one of my favorites. For those of you who doesn't know, LangChain is a Python framework to do machine learning and LLM workloads. So it's just a framework to be able to integrate with like OpenAI or Google Cloud or whatever AI provider. But LangChain itself is a very cool framework because it has some built-in features that are LLM provider agnostic. So it has features that are not specific to Google Cloud or to OpenAI or to whatever. They are features that most developers who does AI need. For example, if you have to write an application that takes as an input a PDF file, right, and then reads the text of that PDF and sends it to an LLM to resume it, or to summarize it, right, very common problem that people are solving these days, the function to extract text from PDF is in LangChain. Because that's something that you would need regardless of which LLM you use, right? So the function to be able to load the doc or to extract text from the doc is built into the LangChain framework. So you could use LangChain to write your applications and then run them on top of Ray. That's what I'm trying to say. And then it supports a bunch of other ones. And in my opinion, this is actually the best, the main reason why we are talking about Ray and Kubernetes at the same time is portability. The fact that you can write Ray frameworks or write Ray tasks or actors or applications that can run on top of Ray, that runs on top of Kubernetes, means that your entire setup is extremely portable. So you can run it on top of Google Cloud. If you're not happy, move to Azure. If you're not happy, move to AWS. If you're not happy, run it on your own platform, right? It would work on OpenShift because OpenShift is just standard Kubernetes. It will run on any Kubernetes installation anywhere. It will run on cloud, it will run on-prem, it will run anywhere. So this is as close as we can get to write once, run anywhere, right? Why am I saying as close as we can get? Well, obviously, the only limitation you're going to have is if your application depends on hardware accelerators. So if you need GPUs, for example, then that's the only limitation you will have with portability, because not all cloud providers offer the same types of GPUs. Some of them has the NVIDIA H100, some doesn't, so you might not have access to the GPUs you need. And those large language models that we are all working on these days, they are pretty GPU hungry. Like the more GPU you give it, the better it runs. The less GPU you give it, the slowest and dumbest it becomes. So if you want your LLM to perform well, normally you have to throw quite a lot of GPUs on it. So this is probably the only limitation that will make porting your Ray applications on Kubernetes difficult between cloud providers, because it depends which one offers what, right? Pretty much everything else will become portable. You write code in Python, use the Ray library, run it anywhere. Talk a little bit about this. I have in the slide a couple of resources. We have actually some links to some guides to be able to run Ray on top of Kubernetes, to write applications in Ray, to do fine-tuning in Ray. So I'm going to share the slides later and you can find them. And yeah, so one of the companies that uses it the most is this company called Niantic. If you are familiar with the game Pokemon Go, you know that game? So these are the guys who built Pokemon Go. And so they are actually one of the people who use Ray on top of Kubernetes. They happen to run it on top of Google Cloud, but that's not very important for the purpose of this presentation. They actually have a link to more details about how they actually use Ray internally, how they enable their data scientists to be able to write workloads in Ray and then run it on top of Kubernetes. And then the episode we published this week of the Kubernetes podcast, the one about Spotify, they also go into details. Like, I didn't do the interview, it was a colleague of mine, but they went into details of how they enable their actual data scientists to be able to leverage Ray, but in an abstracted way, so that people don't really actually even know that it's Kubernetes under the hood. They just write Ray workloads, push them somewhere, and then pipelines get executed, and it's not anybody's problem. The framework is growing quite a lot. This is on our cloud platform. We have like a growth of about 37% every month with people who use Ray. And we know because we have visibility into the clusters, so we can know what people are running inside the clusters, and we can know if it's Ray. The framework itself had 5 major releases, not 4. This is an outdated slide. So there have been 5 major releases. The Ray exists since 2 years, honestly. It's not very old. It has like quite a lot of contributors from all over the world, so it's a very, very stable, very mature framework. And yeah, it has like references everywhere, like Spotify, as I talked about. There's like some articles on the internet. DoorDash is also a user, and a bunch of other companies. Instacart is users. A lot of other companies are using it actually internally. And with that, I have one more. Yeah, so there is like I'm gonna show it there. 1 second. Yes, this is actually like an end-to-end demo that we have that uses an open source pre-trained LLM from Meta. And it has, like, the link is in the show notes, but this has like end-to-end example of doing like data preparation, data ingestion, fine-tuning, serving, and writing an LLM application that integrates with the machine learning model. So you have a full guide on how you could do the stuff, so you don't have to start from scratch. You can use existing stuff. And I think with that, that's all I have. There is another example that you can also find which uses Gradio and LangChain for J. So all of these are in the show notes, so you'll be able to find the links there. And with that, thank you very much. Gracias. Do you have any questions? You could try to ask them in Maltese, I probably understand. Oh, so either no one understood what I was talking about, or it was very clear. Yes?
Yeah, so using LangChain with language graph.
Sorry, using LangChain with?
Chain graph. And now I would like to deploy in an agent. So how I can use your SGHIOUAR or your framework to able to deploy. And I have massive data, right? And I have a workflow with multiple agents talking to each other.
Yeah, maybe with microphone is better. So you use LangChain for J with LangGraph?
Yes. And I have like multiple agents, and this agent responsible to indexing or try to vector multiple documents or sites from SharePoint. And I needed, when you come to me and say, okay, I'm looking for this kind of information, I will get back to you and say, yeah, this document is absolutely fit your requirement, or this is like 100%. And this agent is not a financial agent only, but we have multiple agents like one for finance, one for F&O, which is Dynamics 365. So how we can handle that with Azure platform? Because in Azure, we already implemented the solutions. We try with the normal things like we have a Kubernetes services, we try to upload it, and every agent running a specific node, and we try to communicate with each other. So how we can replace these solutions with Ray API?
Okay, I'm not very familiar with Azure, so I don't know much about what solutions they have on Google Cloud. But to solve your particular problem, what I would probably do is I would look into building a RAG, Retrieval Augmented Generation application. So a RAG in LLM space is a technique by which you run an LLM, but you give it an external source of data. And you tell it that for certain requests, you can talk to this external source of data. The external source of data is typically a vector store, so a vector database that stores vector. So how would that look like for you? Is you would have to write a pipeline that takes all these files, these are the source, like extract the text from the files, chunk them into vectors, and then store them in a vector database. Which vector database do you use? It's like there is tons of examples on the internet. If you want to keep it simple, you can just use Postgres, and Postgres has a plugin called PG Vector, so that turns Postgres into a vector database, right? By the way, all of this can be used. You can use LangChain for this. So you can use LangChain to load the PDF files or text files or whatever the files are, extract the contents, and then turn it into vector embeddings. They're called. Store the vector embeddings in a database, and then run whatever model you want, whatever agent. It's a model, right? And with that model, you can just tell it, hey, there is an external database. So depending on what the user prompt is, it will be able to consult this external database, and from there find metadata about which file that text is coming from. That's how I would solve this problem. Make sense? Like you could use Ray to orchestrate all of this. So the code itself, you could just run it in LangChain to be able to load the. I mean, you will have to get a way for you to be able to get notified for when new files are added, so you can trigger the pipeline to be able to read the text from those files. So that depends on where those files are stored. You might have probably some notification mechanism to be able to say like new file added, so then I'm gonna load it and then extract the vectors and store them in a database.
And so once the workflow started, so I get a notification from the agent.
Yes.
So I have like a scalable message. So every agent run, give me a message, okay, I finished my job and this is the result.
Okay.
Yeah,
so you have a notification mechanism.
Somehow you are not able to track this agent is returning a result or not, because we have multiple agents running parallel, so this is a problem or something.
To be able to know what the output of the agent was?
Yeah, to track every agent, yeah. Like I have like 5 agents. All these agents have returned an 8 or not.
I mean, store them in a database. You can just store the output in a database.
Yeah, but the goal is it's maybe to sort of understand, to make sure at runtime which one is responding to you, and if I have agent based on another agent.
I see. It is a very common issue. Well, the problem is I'm not familiar with Azure, right? Because on Google Cloud we have a way to build agents, and it's super simple on our platform. But obviously you're not going to be able to migrate. So I'm not trying to sell you Google Cloud here. I'm just saying. So I would, generally speaking, I would explore RAG, just retrieval augmented generation. That would be the technique to be able to extract text from files and get an LLM to basically use an external vector store to be able to get like more data about what the question is. Does it make sense? Right? Thank you. There's any other questions? Well, if not, then thank you very much. Grazie.